Have you ever written Python code that, works perfectly, but it just runs painfully slow? You upgrade your hardware, you throw more CPU at it, but the program is still dragging its feet. Well, today we are dismantling the engine of one of the world's most popular programming languages to see what's actually going on inside. We're popping the hood on Python. It's a really common frustration. You write this pristine, elegant script, but when you run it alongside C, Java, or heck, even JavaScript, it feels like it's just crawling. And honestly, this leads a lot of developers to mistakenly believe the language is just poorly implemented, or maybe that the core developers just don't care about performance. But, as we're going to see, the truth is deeply embedded in how the language is fundamentally designed to work. Look at this profound insight from the source material. Executing Python is more similar to rendering HTML than it is to executing JS. I mean, think about that for a second. Python's bytecode isn't an explicit step-by-step machine instruction manual. It's more of a high-level description of what the runtime should do. Just like when a browser reads HTML and has to do a massive amount of interpretation to figure out how to actually draw the page, Python operates in that exact same highly interpretive way. So here's our architectural blueprint for today's teardown. We're going to look at the Python speed paradox, the cost of dynamism, boxing and memory overhead, the infamous global interpreter lock, and finally, why being optimized for human time makes all of this a brilliant trade-off. All right, starting with part 1, the Python speed paradox, and spending time in the C runtime. Here's the crazy paradox. To understand why Python is slow, we have to look at what it's actually doing. And it turns out Python spends almost all of its time not in Python code, but in the C runtime, executing extremely heavy instructions. Python opcodes, the basic instructions the interpreter reads, are what we call fat. They're incredibly complex. The cost of actually executing these fat instructions completely dwarfs the time it takes to just fetch them. This is exactly why just slapping a just-in-time compiler on it often doesn't solve the core speed issue. You aren't trying to speed up simple instructions. You're essentially trying to optimize complex C code, which is, well, incredibly difficult. Moving on to section 2, the cost of dynamism and the burden of extreme flexibility. So, what's the unseen labor behind a fat opcode? Imagine a simple variable assignment, something like object.name equals value. In a lower-level language, that's practically a single step. But in Python, it requires an entire checklist. The interpreter has to check if the top of the stack is an object, check if writing to attributes is even allowed, verify the attribute name is a string, and then finally execute a dictionary update, which, by the way, might trigger an expensive hashmap resize. All of this happens because the interpreter fundamentally cannot trust the input. Let's compare this directly. A thin instruction set in C or C++ can just trust the compiler. It boils down to a single load-effective address instruction. But Python takes a totally different path. It has a strict mandate from its creator to literally never crash on nonsensical input. That forces the system to constantly validate everything at every single step, slowing down the overall execution. It's basically the difference between flying down an open highway at top speed versus having to stop at a toll booth every 100 feet. Next up, section 3, boxing and memory overhead, or the heavy weight of simple math. This brings us to a really fascinating concept called boxing. Because Python is so intensely dynamic, it can't just use raw, lightweight hardware integers like C does. Instead, it has to box them. It literally takes basic primitive numbers and wraps them inside fully allocated memory-heavy objects. Every single time you create a simple number, Python is triggering memory allocation and adding to your garbage collection overhead. So what's the real-world impact of that? Well, 6. Due to this boxing overhead, calculating the sum of 100 million floating-point numbers in Python can actually be up to 6 times slower than executing that exact same loop in JavaScript. Now, JavaScript engines have poured massive engineering resources into unboxing these primitives, but Python's strict dynamic semantics make that kind of optimization incredibly difficult to pull off without breaking existing code.
Let's jump to section 4, the global interpreter lock and the concurrency bottleneck.
Okay, it's time to talk about the most infamous component of the Python engine. We're talking about the GIL, the global interpreter lock. The GIL is a threading mechanism that physically prevents multiple threads from executing Python bytecodes at the exact same time. Now, it was originally included because, frankly, it was simple to implement, and it kept memory states highly stable and safe from corruption. But the major downside, it strictly prevents true parallel execution of Python code on modern multi-core processors. You literally cannot run 2 Python threads on 2 different cores at the same time. Now, developers often try to cleverly bypass the GIL using multi-processing instead of standard native threads. But here's the catch with that. Passing objects between these entirely separate processes becomes painfully slow. Why? Because the data has to be serialized, or what Python calls pickled, sent across the process boundary and then unpickled on the other side. This causes heavy memory duplication and massive overhead. It often entirely defeats the purpose of trying to speed up the application in the first place.
Which brings us to our final point, Section 5. Optimized for human time, the intentional engineering trade-off. Because here is the big plot twist of this whole explainer. After hearing all of this, you might honestly think Python is simply broken. But these seemingly slow mechanics, they are actually deliberate, brilliant engineering victories.
Check out this quote. Python is high-level glue between efficient C functions. You see, Python was actually never meant to do the heavy computational lifting itself. It acts as a highly expressive, easy-to-read orchestrator for lightning-fast native libraries. When you use tools like NumPy, Pandas, or PyCuda, the actual heavy lifting drops down into optimized C, C++, or Fortran code. Python, it just acts as the friendly steering wheel.
Python makes incredibly intentional choices. A simple grammar, simple data structures, and a highly accessible C-Python runtime. The original creator prioritized the simplicity and dynamic expressiveness, knowing full well that a highly complex, difficult-to-maintain implementation would just abandon the language's founding principles. It absolutely prioritizes a crash-proof, flexible experience over raw machine speed.
So what is the grand trade-off here? It's simple, really. Python essentially trades cheap computer processing cycles to save incredibly expensive human development time. It empowers teams to rapidly ship complex ideas. It acts as a low-friction glue for those heavy-duty C libraries. It focuses entirely on human time, not machine time. Yes, your server might have to work a little bit harder, but your engineering team is going to finish that product weeks or even months faster.
Ultimately, digging into this engine reveals that Python isn't failing at all. It's succeeding brilliantly at what it was actually built to do. So I'll leave you with this final thought. Instead of asking why your Python code is slow, maybe ask yourself, are you writing your computationally heavy logic purely in Python? Or are you stepping back and using Python as the masterful glue it was always designed to be? Just something to think about the next time you hit run.